welcome back to my channel. Today we're going to be looking at the multiple choice section of the specimen paper. You can find the specimen paper on the SQA website and I've linked it down below. It's not found in the past paper drop down menu but instead on the advanced higher chemistry page. If you haven't already done this paper, I would recommend that you go to that link and try the multiple choice section and use this video to help you mark it. So here's looking at question 1. So we have an element X and it forms an ion X3+, which contains 55 electrons, and we're to find which block of the periodic table that X would be in. So if X3+ has 55 electrons, then X must have 58 electrons as it's lost 3 electrons. If you then look up number 58 on the periodic table, you'll find that that is cerium. So if I draw a quick sketch of the periodic table and the blocks that we have, so this first block here, the last orbital to be filled is an s orbital, so this is the s block. This block over here, the last orbital to be filled is a p, so that's the p block. In the middle we have the D block, and at the bottom we have the F block. If you look for cerium on the periodic table, you'll find that it's in the F block, so that means that the answer to this question is D. Question 2. So we're trying to find which of these metal salts will emit radiation of the highest frequency when placed in a Bunsen flame. Highest frequency, we are looking for the smallest wavelength. If you have a look on page 15 of the databook, you can find the flame colours and the associated wavelengths for each of these. So copper is 522 nanometers, potassium is 405, barium is 554, and lithium is 671. That would lead the answer to be B, potassium chloride. The answers state that it's A, however I feel that this must be incorrect. So here we have a picture of a molecule and it has a square planar structure. What we have here is a central atom and then 4 bonds, which are being shown as wedges, and these are our bonding electron pairs, and then 2 sets of lone pairs or non-bonding pairs, one above and below the plane of the bonds. So for each of these species we have to work out which one of them would fit this structure here. So what we have is 6 electron pairs, 4 of which are bonding and 2 of which are non-bonding. So if we go through the VSEPR rules to allow us to calculate which of these molecules fits this particular arrangement. So sulfur has 6 outer electrons and we have joined 4 atoms to it and we have no charge, so that gives us 10 electrons. If we divide that by 2, we have 5 pairs, so it can't be this one. If we take the next one, we've got nitrogen, which has 5. We've joined 4 things on and we take away 1 for the charge, so that gives us 8 divided by 2 is 4 electron pairs, so that can't be the answer. Xenon has 8 electrons. We've joined 4 things on and we've got no charge, so that's 12. If we divide that by 2, we have 6. So far this is the only one that could be possible. If we take away the number of things which are attached, which is 4, that gives us 2 non-bonding pairs. So that tells us we have 4 bonding and 2 non-bonding, so this should be our answer. And then if we just try and eliminate the last one, we've got aluminium, so that's 3 plus 4. The charge is quite hard to see, but it's a -1. So that gives us 8 divided by 2 is 4, so that can't be our answer. So our answer here is xenon tetrafluoride. For this question we're trying to write the formula for the name of a complex ion. So we've been given the name here. we've got hexaamine nickel 2. So the first thing we need to do is to work out what the charge on the complex ion would be. As this ends in nickel and not nickelate, then it must be positive as our charge, so C cannot be the answer. Amine has no charge, it's a neutral ligand, and your nickel has a 2 here, so it's a 2+. So it has to be a 2+, so we've got 3 options to look at there. So then now we're having a look at the formula for amine. So formula for amine is that of ammonia, so it's NH3. So that means that our answer is B, NiNH3 6, 2+. So for this one here, we need to do a bit of a calculation. So you need to be able to write out your K equation for this equilibrium. So it's going to be the products on the top and then the reactants on the bottom. So we've got the concentration of methane multiplied by the concentration of water, which is included in this case because it's a gas, not a liquid, and then divided by the concentration of carbon monoxide multiplied by the concentration of hydrogen raised to the power of 3 because of the 3 here. Now you're given the value of K, which is 3.9, and then you simply have to substitute in the values from the table that you have here. So we're trying to work out the concentration of methane. You would then rearrange this for the concentration of methane. And then when you calculate that out, you'll find that the answer is 4.9 times 10 to the minus 5, which is C. So this question here is making sure that you know all of your definitions about acids. So we have an aqueous solution of ethanoic acid. So ethanoic acid is a weak acid, and we're diluting it. So whenever you dilute any acid, you are reducing the concentration of H+ ions, which means that the pH will increase. So the pH A there can't be the answer. Looks like H+ concentration will be our answer, as it will decrease. pKa and Ka are linked. They are constant for your acid. They are just your equilibrium constant and then the minus log base 10 of your equilibrium constant. So diluting the acid won't have an effect on either of those. There is B. So question 7, we need to do a calculation for this, and you can find the equation at the front of your databook. The equation that we're going to use is pH equals pKa minus log of concentration of acid divided by concentration of salt. So to find the pKa, you can look at page 15 of your databook, and you'll be able to find the pKa for ethanoic acid. If you look that up, you'll find that it's 4.76, and we're going to do minus log of our concentration of acid, which is 0.1, and our concentration of salt, which is 0.2. And if you calculate that through, you'll find that the pH is 5.1. So your answer is D. This question is again looking at acids, this time looking at indicators. So you have ammonia reacting with hydrochloric acid, and you're showing the pH curve for that reaction. And you're to find which indicator would not be suitable to be used for this reaction. So a suitable indicator has to have its pH change over this straight part here. Now ideally it would be in the very middle of that part of the line. So if we have a look at the numbers that we have here, so methyl orange has a pH range of 3.1 to 4.4, so that's within this part here. Bromophenol blue is 5.2 to 6.8, so again in this straight part here. And bromothymol blue has a range of 6 to 7.6, so again on the straight part. Phenolphthalein is 8.3 to 10, which is above the straight part of the curve, so phenolphthalein would not be a good indicator to use for this reaction. So another question looking at your knowledge of acids. So you have ethanoic acid is a weak acid and hydrochloric acid is a strong acid. Which of the following is not true? So we just need to take each of these in turn and work out whatever is required. So to work out the pH of a strong acid, such as hydrochloric acid, you do negative log of your concentration of H+, which in this case is going to be the same as the concentration because you have one H+ ion for every mole of hydrochloric acid. And when you work that through, you'll find that that is pH 1, so that is true, so that can't be our answer. We have 20 centimetres cubed of 0.1 molar sodium hydroxide is exactly neutralised by 20 centimetres cubed of 0.1 mole ethanoic acid. So this would be a 1-to-1 mole relationship if you were to do this reaction, which means that you would need equal volumes of the two, so that one is true. pH of 0.1 molar hydrochloric acid is lower than that of 0.1 molar ethanoic acid. This is true because the pH of a strong acid is always lower than that of a weak acid because you have more ionization and therefore more H+ ions. So that leaves us with D. The Ka value for ethanoic acid is greater than that of hydrochloric acid. So your Ka value is your concentration of H+ ions and A- ions divided by your concentration of the acid that you started with. So for a strong acid, it almost completely dissociates, so the top line dominates, so you end up with a very large Ka. However, for a weak acid, you find that the bottom line is smaller. However, for a weak acid, you find that the bottom line is larger and therefore you have a very small Ka value. So the Ka value for ethanoic acid would not be greater than that of hydrochloric acid, so that is the answer. You need to read these questions really carefully to make sure that you're looking for the right things. Question 10. The standard enthalpy of formation of strontium chloride is the enthalpy change for which of the following reactions? So you need to know the definition of this. So the standard enthalpy of formation is the formation of 1 mole of substance from its elements in standard states. Now you can use your data book to find the melting and boiling points of different elements, so you can work out what state they'll be in at 25 degrees, which is the standard states. So all of these are making strontium chloride, which is SrCl2 solid, so we need to work out which of the reactants is the correct one. So strontium is a solid at room temperature, so it could only be B, which also has chlorine as a diatomic gas. So here we're looking at entropy. Entropy is disorder. So to have the greatest entropy, you need the greatest disorder, which would generally mean that something is a liquid or a gas. If we have a look at page 8, if you have a look at page 9 of your data book, you can find the boiling points of these substances. So the boiling point of propan-1-ol is 97, the boiling point of butan-1-ol is 118, the boiling point of propan-2-ol is 82 and the boiling point of butan-2-ol is 100. So if we're at 90 degrees, propan-1-ol, butan-1-ol and butan-2-ol are all still liquids, whereas propan-2-ol has boiled, which means that it's now a gas and therefore has the greatest entropy. I have a question where you have an equation to use to allow you to calculate the boiling point of a liquid. Now bear in mind that they are expecting you to use this equation to calculate the boiling point of water, and you might already have ideas of what that might be, but make sure you do the actual calculation. When you're looking at the values that you have here, you need to make sure they're in the same units. You have two options. You can either turn your entropy value into kilojoules, or you can turn your enthalpy value into joules. I prefer to turn the entropy value into kilojoules. So to do this, I'm going to do 88 divided by 1000 first, and that's equal to the 40.6 divided by the boiling point. If we then rearrange, then we find that the boiling point of water using this equation is 461 Kelvin, which is D. The other values are there to throw you, and you would be able to get any of the values using different ways of using the equation. 373 is what you would maybe expect it to be, and the other values would be, you would be able to get those by using 88 joules instead of kilojoules. So be careful with the equations. Okay, this one here is about kinetics, so the order of a reactant in a reaction. We're just going to go through each of the statements. So can only be obtained by experiments. So the order of reactants, when we look at those, we look at doubling the concentration of the reactant and then what happens to the rate. You can only do that by experiment. The order of a reactant in a reaction determines the speed of an overall reaction. By itself it can't, it does need the other reactants, and you need to know something about thermodynamics to know how fast it's going to go. Is determined by the stoichiometry involved, that has no effect on the order, and is the sequence of steps in the reaction mechanism. You would need all of the reactants to know that. So your answer is A. So here we have a mechanism, so your overall reaction is 2x plus y to give you x2 plus y. And it's a two-step process. The first step here is x plus y to give you xy as an intermediate, and that's a slow step. And then the second step, xy, reacts with the second mole of x to give you the final product, and that's a fast step. So which mechanism is consistent with the mechanism is consistent with which of the following rate equations? So the rate equation is based upon the slow step, so that's this one here. And it looks at the reactants only, and it is the stoichiometry of this reaction here. So we have x and y, and we've only got one of each. So the rate equation that would apply would be B, where we have 1 mole of x and 1 mole of y. For question 15, we're going to do a calculation. So we're trying to find the volume of potassium sulfate that we would need if we were going to dilute to make a specific concentration. So potassium sulfate is K2SO4. We're looking at the potassium ion concentration of the new solution that we make. And we want to know what volume of the original solution we would need. So we're making 1 litre of a solution, and it has a concentration of 0.1 mole. So we can work out how many moles we would have using moles equals C times V. And your volume is already in litres. Now that gives you the number of moles of potassium ions, so that's K+. And if we have a look at our formula here, 1 mole of potassium sulfate would give you 2 moles of K+. So to work out how many moles of potassium sulfate we require, we need to divide this by 2. and then we can rearrange the equation to allow us to work out volume. So we know now we need 0.05 moles of potassium sulfate solution, and the concentration is 0.2. Which gives you a volume of 0.25 litres. All of the answers are in centimetres cubed, so you need to times by 1,000 to give you 250. So your answer is C. Here we're now looking at some Unit 2 work. So the end-on overlap of two atomic orbitals lying across the axis of a bond leads to what? So that would be something like this. If we take two pi orbitals, if we take two p orbitals and overlap them, so the bond is going this way. So hybridization is the mixing of orbitals, so it's not going to be that one. A sigma bond is always along the axes. Pi bond is where it would be up and down, so sideways overlap with the bond being here. And a double bond is where you've got a sigma and a pi. So our answer here is B, a sigma bond. So question 17, we're looking at nucleophilic properties. So you need to know the definition of a nucleophile. So that is attracted to regions of positive charge. To do that, it needs to have a lone pair or a negative charge. So sodium does not fit the definition of a nucleophile. Br plus is already positive, CH3 plus is already positive, whereas ammonia has a lone pair on the nitrogen, so would be able to act as a nucleophile. This question shows you a reaction mechanism to give a certain product. You're now going to start from a different product and work backwards to work out what you started with. So you need to draw out the structure for 2-hydroxy-2-methyl-butanoic acid. Now ideally you want to draw it in this same way here so that you can compare what you've got. So if we put the acid group at the bottom here, and then we draw in our carbon chain, I'm just going to draw it across there. On the second carbon you have an OH, and you also have a methyl group, and then the rest you just fill in the hydrogens. So now if we work back to this step here, then we would be replacing this group here with the CN group. Now I'm just going to show the carbons, I'm not going to put in the hydrogens just now. Right, we still have our OH there, and then the two other carbons. And then if we now work this back to this starting point, you can see that we had a C double bond O, which then broke open so that you would have an H join onto the oxygen, and then the other carbon for the CN would come down. So if we take this one back to that, we're still going to have our two carbons here, we're still going to have our CH3 here, but we must have had our double bond O here to allow that to open out into the hydroxyl and nitrile group. So now we want to name this, so we've got 4 carbons, so it has to be butanol or butanone, and the double bond is on the second carbon there of this chain, so this one must be butanone. This one here, we're looking for a tertiary haloalkane. So a tertiary haloalkane would have your CX bond, and then your carbon is joined to 3 other carbon groups. So you want to find one of these which would have the correct structure. So a simple way of doing this would be just to try and draw them all out. So this one here has 3 halogens, which is not what we want. The brackets here are branches, so we've got 3 CH3 groups attached. That makes B our answer, as it looks just like this drawing here. Okay, so we've got the structures of 3 alcohols, P, Q and R, and if you have a look at the structures, we have one hydroxyl group, two hydroxyl groups, and then three hydroxyl groups. And you're looking for a line in the table which describes trends in boiling points and viscosities. So this is very much based on knowledge from higher. So increasing the number of hydroxyl groups will increase the strength of your intermolecular forces, which means that your boiling point will increase and your viscosity will increase as well. So the answer is A. Okay, here we've got a little bit of text about a specific synthesis called the Williamson synthesis for making ethers, and it shows you the two steps, and you are given your reactants and you're trying to find what ether would be formed. So you would be best to just insert a diagram of each into the reaction steps and then work out what is produced. So for step 1, we take our alcohol, so for us that's propan-2-ol. So I'm just showing it without the hydrogens for clarity. So we've got 3 carbons, and on the second one we have our OH group. And when we react that with sodium, we make an alkoxide. So we have a negative charge on the oxygen, and we've got sodium there, and we'll also give off some hydrogen gas. This is then reacted with our haloalkane, which in this case is chlorobutane. So if we draw our 2-chlorobutane, here's our butane, and on the second carbon we have a chlorine. So we are substituting this chlorine for this group here. So if we draw that out, you can see that we've taken away the chlorine and we have added on this alkoxide group. Now these have all been drawn out in terms of shortened structural formula, so we need to find one which would fit. So here, this part here would be for propan-1-ol, so that one cannot be correct, as is this one here. If we look at the next one, we have a CH3 and then a CH, and then that CH has a chain on it to allow it to join on to the oxygen. However, on the other side, this would be a straight chain. This would be for 1-chlorobutane, so this one can't be correct either. Whereas here we've got that same chained propanol group, but then we've also got a chain on the butane, so D is the answer. So here we're looking at reactions, and we have 3 reactions to have a look at. So we're starting from propan-1-ol. So we have 3 carbons with an OH on the end, and then we are going to 1-chloropropane. So we have exchanged the OH for a Cl, which is a substitution reaction. So we can only have A or B as our answers. And then we're going from our 1-chloropropane to propene. So we've removed the Cl and an H from the molecule to produce a double bond, and then here we have taken the Cl and replaced it with an OCH3. So for the second step we have eliminated some atoms, and for the third step we have substituted. So A is our answer. Here we're looking at planar molecules, so if we draw them out with a little bit more detail, you'll be able to see which ones are planar. So a benzene ring itself is always planar. So you have a ring of 6 carbons with hydrogens attached to each. One of these has been substituted for a chlorine in this case, but it's still planar, and you've got the ring of electrons above and below, so that one's planar. here we have something based on ethene, which is also planar, so all of these bonds are within the same plane, so they're all 120 degrees from each other. And then we have another alkene here, which you may expect to be planar. However, if we draw this molecule, this side of the molecule here showing the shape, you can see that this group here has a three-dimensional shape based on a tetrahedral. So that means that R is not planar. So our answer is C, P and Q are our only planar molecules. Okay, so for this question we're looking at compounds reacting with hydrochloric acid. For something to react with hydrochloric acid, it needs to have a basic group. So amines are weakly basic, so we'll react with hydrochloric acid. So we have one NH2 group here, we have one on this one, we have two on this molecule, and we only have the one here. So our answer will be C because we have the most basic groups there. For this question you need to use your data book, and you're looking at page 14 where you'll find the infrared absorption table, and you're looking at 330 to 350 per centimetre, and that is an amine NH group. So if we look at each of these structures here, we have a tertiary amine, so there's no NH groups. For B there is an NH group, so that one would show the absorption. This one here has two NH groups, so that would show absorption, and this one has NH as well. So our answer is A, the tertiary amine. Okay, question 26 is looking at reactions of benzene rings. So here we have bromine and we have AlCl3. That is acting as a catalyst, so this reaction can take place. When you've got bromine with light, you're looking at doing a free radical reaction and substituting. However, that's not possible with the ring, so that won't happen. However, substituting onto the CH3 group can happen. And then here you've got sulfonation. So the reaction that can't happen is B. Okay, so we're looking at different analytical techniques, so you need to know what each of these can be used for. So mass spectrometry is good for finding fragments of organic molecules. Sodium ions in a urine sample wouldn't really be able to be found. Infrared will give you functional groups. So again, used for organic molecules. Atomic emission spectroscopy, this was looking at the intensity of a flame colour. So you could use this for sodium ions as it would give off a yellow light, and you could measure the intensity, which is linked to the concentration. And proton nuclear magnetic resonance spectroscopy gives us connectivity of atoms in organic molecules. So the best one to use to find the concentration of sodium ions is atomic emission spectroscopy. Okay, question 28. We're looking at hydrolysis of haloalkane, and you're finding that it's done by SM1 mechanism. So this is substitution, nucleophilic, and it's first order kinetics, which means only one molecule in the slowest step, and that is your haloalkane. So what happens here, if we draw this out, we have your haloalkane, and this one is tertiary, and they often go by SM1 reactions. As nothing can attack this, your bromine here can come off to create your carbocation. In the process, this rearranges so that we have a trigonal planar arrangement of bonds, which means that your answer here is A. Okay, so for question 29, we're going to be using the n+1 rule, where n is the number of hydrogens on the neighbouring carbons, and then you add 1 on to find how many lines will be shown for that particular group. So for HA, we have 1 hydrogen here on the neighbouring carbon, so that means that we'll have 1 + 1, which is 2 lines. For B, we've got 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 hydrogens on neighbouring carbons, and +1 would be 9 lines seen. For C, we have 1, 2, 3, so 3 + 1 is 4. And then for D, we're only looking at the hydrogens on neighbouring carbons, so we've got 2 hydrogens there, so 2 + 1 is 3. So this would be the one to show this particular splitting. So HD is our answer. Okay, the final question, we're having a look at sulfonamides and their activity. So these are a type of drug, and we need to work out which of these particular drugs here would be active. So you've been given 2 active drugs and 2 inactive drugs to have a look at the structure of. So we're going to highlight what is the parts which are required. So if we have a look at the structure of the 2 active drugs and what is similar between those, so they both have this NH group here, they both have this ring, they both have this SO2 part, and they both have this NH. This part here is changed, but they're both active, so this part just changes slightly how it will work, but they both work. If we then have a look at the inactive drugs and find the parts which are missing, so here this one has the NH2 group, it has the ring and it has the SO2, but it doesn't have the NH group, so missing that part means that it's no longer active. And this one here has a similar structure from this end to this very first one, but then at this part here it's got a CH3 group rather than an H, so that must make this one inactive. So we need to have a look at the molecules and find where they are similar to the active ones. So this one has the NH2 group, it has the ring, it has the SO2, and it has the NH, so we would imagine this will be our answer. This one here has that CH3 group, which seems to make that one inactive, so this one is probably not going to be right. This one here has the NH2 and it has the ring and it has the SO2, but it's missing the NH at this end. And this one, like B, has the CH3 group here, so this one is also inactive. So our answer is A. Thank you for watching my video. I hope that you found it helpful. Please remember to subscribe and follow me on Twitter @MissAdamsChem for regular updates on new videos. Bye for now.